It's an honor to be here today. I'm just very grateful to have been asked to give this lecture on behalf of my department, Physics and Astronomy. I'm a relatively new faculty member here at UCI, as you heard, and I have received the warmest of welcomes from all directions on campus, especially from our school and my department, where I've been ecstatically welcomed by its faculty, postdocs, and students. And I'm grateful, and I'm excited to be a part of this community. I feel like I have to address Ken's question of, like, why did I go and get an MFA in acting? So in a nutshell, I love telling stories. And I was at a crossroads when I was in an undergrad at MIT because I loved the stories that I could tell as an actor, that I had started to do more acting in high school. And so I loved kind of entering a world and inviting people in the audience into that world. And I also loved the universe and the story of the universe that's continuing to unfold as we continue to live within it. And so I was at a crossroads, but I've found a way to be able to combine the two. And what I hope to do today is tell you a story of exoplanets and of the search for the next habitable planet and life beyond the solar system. And I'm going to specifically talk about how I and my team are contributing to that search. This is one of my favorite images. It's from the Apollo 17 mission, which was the last manned mission to the moon in 1972. Our planet orbits one single middle-aged star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. I love this image. It comes from the Hubble Ultra Deep Field team. And so if you look at this image, you might at first glance think that these individual points of light are stars. But no, they're actually each individual galaxies. There are over 10,000 galaxies depicted here. And this exposure was collectively taken over 11.3 days. And it's one of the deepest visible light images ever taken of our universe. And each galaxy carries within it billions, and in some case, hundreds of billions of stars, like our own galaxy does. So just thinking about what that might mean for life elsewhere is something that is very exciting to me. So I'm going to take you back to a time in the not too distant past, at least from my vantage point. As I get older and older, it seems to be more and more distant. But for those of you who might be college students in the room, this year is going to seem like prehistoric times. The year is 1995. And those college students I taught last fall, many of them were not born yet, and that just blew my mind. So this year marked the discovery of the first planetary mass companion orbiting another main sequence star. And for the non-astronomers in the room, when I say main sequence, I mean a star that, just like our sun, is undergoing the process of nuclear fusion in its core. It's just chugging away, burning hydrogen into helium. So this planet was found orbiting a star like the sun, and that star is called 51 Pegasi. And the planet found orbiting it is 51 Pegasi b. Usually they're given the letter B as the first planet that's discovered, and the star is sort of A, but we don't actually use the letter A. We just give it that name. This planet was found using the radial velocity, or Doppler technique, which measures changes in a star's velocity due to the gravitational tug of an orbiting planet. So as the planet orbits the star, you can see that they're actually both doing a little orbit. They're orbiting around a common center of mass between the two, which happens to be much closer to the much more massive star. And this orbit, this wobble that the star does, is directly proportional to the mass of the planet orbiting it. This method is particularly sensitive to large planets orbiting very close in to their stars. And this planet that was found in 1995 was actually found to be closer to its star than Mercury is to the sun, with a minimum mass about half that of Jupiter. So not very Earth-like by comparison. By the end of the 20th century, several dozen planets had been discovered orbiting other stars and called extrasolar planets, or exoplanets for short. So we're going to jump ahead almost 20 years to the year 2014, and this year marked the discovery of one of the smallest planets yet, Kepler 186f. And this planet is only about 10% larger than the Earth. And it orbits in a closely packed 5-planet system around a very cool, small, red star. And as its name would suggest, Kepler 186f was found using NASA's Kepler mission. Now, Kepler uses a very different technique than the radial velocity or Doppler technique. It uses the transit technique. And this technique finds planets that pass in front of their host stars from our vantage point. And they block out a little bit of the star's light, and that allows us to determine the size of the planets. That amount of light that's blocked out is directly proportional to the size of the planet. So if we were to look at exoplanet discovery over the years, we can see that the number of exoplanets discovered has just exploded over the last 5 to 6 years or so. And that's largely due to NASA's Kepler mission. So that we now have a current planet count of over 3,700 planets that have been confirmed orbiting other stars within our own galaxy alone. And that spans the gamut in terms of the types of planets. We have gas giants like Jupiter, we have Neptune-like planets, we have what's called super Earths, which are a little bit larger than our Earth, and we have terrestrial-sized planets that we've started to discover. But of this nearly 4,000 confirmed planets, only a very small subset are what we would term potentially habitable exoplanets. And this number fluctuates between a dozen, maybe bordering on 24, depending on who you ask. Because the criteria that we use to call something potentially habitable, and of course even habitable, varies. And I'll talk more about that shortly. So if we were to look at progress that we've made in exoplanet discovery on one single slide, here it is. This is that first planet that we discovered in 1995, Jupiter scale. And this actually is what's called a hot Jupiter because it orbits so close to its sun, to its star, that its atmosphere is most likely being stripped away due to all that heavy, intense energy it's getting from its star. And so nearly 11 times the size of the Earth, to now one of the smallest planets discovered, Kepler 452b, also part of that subset of planets that's been found with the Kepler mission, which is 1.5 times the size of the Earth. This in itself is a huge discovery milestone that we've made just due to observational instrumentation, and that's incredibly important to acknowledge. In the last couple of years, we've also seen several new exciting planetary systems that can be added to this list. Proxima Centauri b, the potentially habitable world orbiting our closest star. So very exciting because it means this planet could actually be characterizable by the next generation of space missions. The 7 planets orbiting TRAPPIST-1, all of which are in the Earth-sized regime, and 2 to 3 of which, depending on who you ask, are in a nice sort of spot away from their star where they might be able to support surface liquid water. And LHS 1140b, such a lovely ring to it, that name is, right? But recently found, and because we have both transit data and radial velocity data, so radial velocity, Doppler technique, that data tells us information about the mass of the planet. The transit technique gives us information about the size of the planet. Put those two together, and we can get information about the planet's density. And that's great because it allows us to, in this case, have some idea of the likelihood of this planet to be rocky. And there's a pretty high likelihood that this planet has a rocky composition. And if you can stand on it, you might actually have oceans on it, right? So that's pretty exciting. All of these individual discoveries in themselves are very exciting. Together, what they do is make a compelling case for the fact that we are moving closer and closer to the holy grail in the field of exoplanet research. The discovery of a habitable planet like the Earth that is capable of supporting and maintaining life over long time scales, and perhaps currently hosting life. We've been finding planets across a diversity of regimes, both in terms of their orbits, in terms of their potential atmospheric compositions, although we don't have exact information about those small planets with their atmospheres just yet, and in terms of their multiplicity, so whether they're alone in their systems or one of multiple planets in the system. Some planets we found are these sort of hot Jupiters. They're orbiting so close to their stars that their atmospheres are being ablated, literally, from the planet itself. Some planets have these very elongated orbits or eccentricities that take them so far away from their stars that if they had oceans on them, those oceans would freeze during the farthest point of the orbit and potentially melt and maybe even boil over at the closest approach of their orbit. And we have planets that have nice, comfortable circular orbits like our Earth, where the planet is completely in the sort of green region, which we call the habitable zone, throughout its entire orbit. And those planets necessarily might be better places to look for life and the long-term presence of a conducive environment for life. With the next mission, the Transiting Exoplanet Survey Satellite, which was just launched in the last couple of weeks, and it was a very exciting and fun launch to watch. I wish I could have watched it in person, but I did watch it on NASA TV. And it is on its way to its orbital location. It is also a transit mission, like Kepler. However, where Kepler just stared at one particular patch of the sky for 4 years and just took picture after picture looking for those dips in brightness caused by transiting planets, TESS is going to be an all-sky survey. It's a 2-year mission. It's going to survey about 500,000 stars, looking for dips in brightness, and it's looking at stars in the nearby solar neighborhood. So they're going to be much brighter, 30 to 100 times brighter than the stars we've looked at with Kepler. And because they're closer, it's going to be much easier to follow up on those planets that we discover with this mission, with the next generation of missions, like the James Webb Space Telescope. James Webb, which is set to launch in the next year or two, is exciting because it's going to allow us not just find planets, but actually start to characterize their atmospheres. Because it's going to carry on its payload a spectrograph. And that spectrograph is going to allow us to measure a star's light filtered through the planet's atmosphere. And when that happens, there are absorption lines that we get in the light from that light passing through the atmosphere. And those absorption lines can tell us the atmospheric composition of that planet. And this spectrograph is an infrared spectrograph, which is great because it's at IR wavelengths that the atmospheric molecules that we're very interested in from a life standpoint, like water vapor, carbon dioxide, ozone, have the largest number of spectral features. And this is all towards the goal of finding a planet that has an atmosphere and an environment similar to the Earth. So I've already thrown out this sort of term of life and conducive to life and habitable. And before we even get into the point where we're able to identify planets that might have life on them, we have to step back for a second and ask that question, what kind of life are we talking about? What does life even need to survive on a planet? And once we can answer that question, then we can go about looking for planets that might have those conditions and therefore likely to sustain life over long time scales. So let's start with what life actually requires to survive and to carry out its own metabolisms and its own chemical reactions. The fundamental requirements for life, at least life as we know it on Earth, include a liquid, which on our planet is water, a suitable environment for the formation of complex organic molecules from so-called bioessential elements like sulfur, phosphorus, oxygen, nitrogen, carbon, hydrogen. We call this sponge for short. And some kind of energy source, whether it's stellar or chemical. So those are the three criteria that a lot of us in astrobiology being the study of the origin, evolution, and distribution of life in the universe, have kind of we've narrowed down to sort of the three most common things that all life on Earth requires. Now, a terrestrial planet, by nature, has some kind of energy source, along with the basic building blocks in some form that are needed for life. But what isn't as common is liquid water. And the reason for that is that it depends on a climate that's capable of maintaining the requisite range of temperatures and pressures that are needed to keep water in liquid form. Life on Earth uses a diversity of metabolisms, but they all require liquid water for chemical bonding and as a solvent for chemical reactions. And therefore, it's liquid water that drives our search for life elsewhere. So, what determines whether a planet falls within or outside of this required temperature range needed to keep water in liquid form? Well, I've already alluded to it, but this so-called habitable zone. One of the first steps that we take when we discover a planet, an exoplanet that could be potentially habitable, what allows us to be able to give it that term, potentially habitable, is that we find it orbiting its star at a very particular location in space. And it's not too close to its star that if it had oceans, they would potentially boil away in a runaway greenhouse state. Not too far away that the oceans could potentially freeze, maybe even the atmosphere freezes out onto the surface. It's just right, and that's therefore the habitable zone is often called the Goldilocks zone, right? Not too hot, not too cold, but just right. So we're going to look at the habitable zone in a different way. So this diagram shows you the habitable zone as a function of the mass of the star that a planet would orbit. So you've got the mass of the star here and the distance away. And so right away, what you can see is that this nice blue swath of space denoting the habitable zone is much farther away from a hotter, brighter star than a cooler, dimmer star. In the same way that you'd need to stand farther away from a bonfire than you would a small campfire in order to get the same amount of heat. So, too close in, the oceans could boil. Too far out, the oceans freeze. So that's sort of the zeroth order step that we take. When observers find an exoplanet, they can calculate based on the amount of energy the planet receives from its star. Okay, the planet is in its habitable zone. Yay, it's potentially habitable. But myself, as a theorist, what I say is that's only the beginning. Because potentially habitable does not mean habitable. And habitable does not at all mean inhabited. Right? We have to make sure that we get these things clear, especially for the media, so that we don't let people think that we've already discovered aliens because we found a couple of exoplanets that are potentially habitable. And the main reason that I sort of like to tout that reality that potentially habitable does not mean habitable is that there are many factors and processes that can affect planetary habitability beyond just orbital distance. If we want one example of a planet that's believed to have experienced a significant climatic event that most assuredly would have impacted the long-term presence of surface liquid water, we don't have to look very far. Here, our Earth, geologic evidence suggests, experienced a very traumatic climatic event about 800 and then again about 600 million years ago. And those events have been termed Snowball Earth episodes. They were termed Snowball Earth by Joe Kirschvink in 1992. And these are events when the planet is believed to have been completely covered in ice from pole to pole. And yet, we know that if this actually did occur several times in our history, photosynthetic life survived. So this scenario is not a disaster scenario for habitability. However, it would be likely much harder for a planet in this kind of a state to expel gases into the atmosphere that we might measure spectroscopically with that spectrograph, like with James Webb, from space, that would tell us that life indeed is there. If that life is beneath a kilometer-thick ice crust, it could be very difficult. And so, yes, you could have life that exists underneath ice, like Jupiter's moon Europa, which is covered in ice. But if that life can't tell us it's there, it might as well not even be there, in my book. So this Snowball Earth episode is just one example of a very sobering truth, and that's that habitability is complicated. So to drive the point home even further, I'm going to start off with liquid water, right? That's what we're looking for. That's what all exoplanet astrobiologists are sort of looking for, planets that might have liquid water, because we know on our planet where there's water, there's life. So what actually governs the presence of liquid water on a planet's surface? Well, it's governed by the radiative and compositional properties of the host star and the planet's individual properties, including its environment. But the picture looks even richer than I've portrayed it here. And in fact, when those of us in this field started to really get specific about all the different processes that come at play when we talk about liquid water, it actually looked a bit more like this. And so you're not meant to try to memorize or read every single block on this slide, but what you're meant to do is to be as overwhelmed as I sometimes feel when I look at this plot. Right? There are a lot of things that are factors when it comes to long-term habitability. The star's activity, its metallicity, how many companions are in a system, how much light the planet receives from the star, but also how its light is distributed across the electromagnetic spectrum, the rotation rate of the planet. I mean, there are just a ton of things, and many things that aren't even on this slide. So with the advent of the TESS mission, we're going to be finding thousands more potentially habitable planets in the coming years. We're not going to be able to follow up on every single potentially habitable world to look for signs of life in its atmosphere. So we're going to need a way to prioritize which planets we can follow up on with James Webb and the next generation of space and ground-based missions, so that we can actually tell, okay, this one is most likely to host life. So that's where I come in. And whereas many people might think of astronomers and astrobiologists who are looking for life as doing what Jodie Foster did in the movie Contact, sort of listening for little green men, and that is certainly a practice as well. The SETI mission is incredibly important, because we never know when we might actually receive technological signals from an advanced to much more advanced civilization, right? That's important to continue with that sort of work as well. My work, though, in this sort of new era where we're actually getting observational data for Earth-sized planets, is developing a new approach. And that's using observational data that we have for those planets in combination with theoretical simulations using climate models. And it's this two-pronged approach that's going to allow us to get a deeper understanding of the likelihood of certain planets to orbiting certain spectral classes of stars to be habitable, particularly planets orbiting sort of small, cool red stars. And so if we were to look at what I do in cartoon form, I take what governs the climate of the one planet that we know to be habitable, our Earth, take the most scientifically interesting planet targets that we have to date, and explore the parameter space, the wide parameter space of stellar and planetary properties which are currently unconstrained and for which observational data are still limited. And that allows me to get a better understanding of the planets that are most likely to succeed in the habitability regime or the habitability contest. And so I've been particularly interested in planets orbiting these cool red stars, and that's for a number of reasons, which I'll start off with in a minute or so. But I want to give a quick primer for those who are not astronomers in the room as to what kind of stars we even have in our galaxy alone, right? So there's a range of different types of stars when you look up at the sky that you see. And this is not the full depiction. There are several other types of stars that are we continue to discover new types of stars already that are even smaller than M stars. But this is the general classification that we have. And these M stars, these cool red stars, are so much smaller and dimmer and less massive than the most massive stars, which are the O stars. You could think of M stars. Well, let me just put on here for scale. Our sun is a G star. So it's that middle-aged star, not particularly big, but sort of halfway through its lifetime currently, right about 5 billion years old. M stars are like the tortoises of the stellar family. Because they're so low mass, they have these low masses, they burn their fuel very slowly. And because they burn through their fuel very slowly, they live for a really long time, hundreds of billions, and in some cases, trillions of years. No M stars have ever died. Their lifetimes are longer than the current age of the universe. As opposed to the O stars, which are the James Dean of the stellar family. They live fast, they die young, and in a few million years, they're gone. Right? Now, whereas the tortoises of the stellar family, the M stars, those 100 billion year lifetimes, in some cases trillion year lifetime, that's really great from a biology standpoint and a habitability standpoint, because it would offer lengthy timescales for orbiting planets to develop life and to have life evolve. Whereas the O stars, a few million years is all that they last, right? And that's not very good for biology, given that it's believed to have taken life on Earth on the order of 500 million to 1 billion years to get a foothold here, right? This is one of the reasons why we're particularly excited about the prospects for life orbiting M stars. Another reason is that most of the stars in our galaxy are M stars. This diagram shows that of all known stars within 10 parsecs, or 33 light years, a light year being about 10 trillion kilometers, of the sun, over 75% of those stars are M stars. So M stars offer the best chance of finding habitable planets through sheer numbers alone. It's also easier to detect planets around M stars with existing techniques, because both that Doppler radial velocity technique and the transit technique is very sensitive to that ratio of the planet to the star. And so a similar sized planet blocks out a larger fraction of a smaller star's light and exudes a larger gravitational pull on a smaller star. And that larger transit depth, that larger radial velocity signal, those are easier to measure. But alas, it's not all sunshine and unicorns when it comes to the prospects for life on planets orbiting M stars. Let's go back to the habitable zone plot. So you probably already noticed this, and that is that the habitable zone is much closer in to those cooler, dimmer stars. And in those close-in orbits, a lot of interesting things can happen. Because you have, even a cool small star is still much more massive than the planet that orbits it. And so that much more massive star is going to pull and push on the planet's orbital period. And it'll slow down that orbital period, and that situation is called tidal locking. You have the planet's rotation period is slowed down, and its rotation period is going to be slowed down potentially so much so that you could actually enter a case of synchronous rotation. This is an extreme case of tidal locking, where your planet's rotation period is slowed so much that its year is equal to its day. And it's always showing the same side to the star at all times in perpetual daytime, while the other side of the planet resides longingly in perpetual night. And that has raised concerns about the atmosphere potentially getting so cold on the night side that the atmosphere freezes out entirely. However, because of climate modeling, we now understand the picture is not potentially as detrimental as we think if you have a planet that's synchronously rotating. We understand now that if you have a thick enough atmosphere on that planet, you could essentially generate enough heat and distribute it to the other side of the planet to avoid atmospheric freeze-out. We also have identified a potential advantage for synchronously rotating planets. If those planets have oceans and they are orbiting sort of perilously close in to the inner edge of the habitable zone where they're in danger of having their oceans boil away, if they're ocean planets, they could develop a cloud layer on the day side. Clouds are very bright, and those clouds could reflect a lot of that incident energy back away from the planet and cool the planet down and essentially buffer it against this sort of runaway greenhouse state. So that's encouraging. Another possible downside for M-star planets is this sort of extended pre-main sequence phase. So if you recall, I mentioned the main sequence is that time when stars are just kind of doing their thing, converting hydrogen into helium in their cores. Before they get to that point, they have this sort of pre-main sequence phase where their luminosities are all over the place, and they're very active. And these active periods for M-stars, because they're so long-lived, could last as long as 1 billion years, during which time you could have tons of high-energy X-ray, UV radiation pelting the surface of a planet. That could be very detrimental to biology. You might have to have life exist at the bottom of an ocean to avoid that harmful X-UV radiation. We also now understand, for those who want even more in-depth understanding of this, is that you could have the oceans completely evaporate away into the stratosphere of a planet and undergo water photolysis, where the water's broken up and the lighter hydrogen escapes to space. The heavier oxygen remains behind to form these so-called oxygen-rich atmospheres. If you measure those from space, you might think, there's oxygen in the atmosphere. Those planets are habitable and have life on them, when in fact those planets could have been long desiccated. So this could actually present what's called a false positive for life. Where I've been most interested and spending most of my time is in the realm of the star's light and how that light is distributed across the EM spectrum, and how that interaction between that light and a planet's atmosphere and surface can affect planetary habitability, particularly when it comes to a process called ice albedo feedback. So we think of ice on our planet, and typically we think ice is very bright. It looks very bright and white. It has a high albedo, which is the reflectivity of a surface. And if you have a high albedo, a high reflectivity, that surface could have an albedo of 0.9 or 1, reflecting almost 100% of the light it receives. Whereas a low albedo surface is something like the ocean, which has an albedo of close to 0. And so we think of light, the more light that ice receives, the colder the planet gets, the more ice forms, temperatures get colder, etc. Right? It's a positive feedback process. However, ice albedo has a spectral dependence. It has a wavelength dependence. And so this ice albedo feedback mechanism is going to be sensitive to the wavelength of light coming from the host star. Ice actually absorbs longer, redder light and reflects shorter, bluer light. And that's why the iceberg in this photo looks blue. So it's receiving light, and the redder light is absorbed on its way through the ice, and it's only the blue light that makes it all the way to the bottom of the ice and it is able to reflect back up to our eyes, and we see blue ice. And so you can see this even more strongly by looking at this picture, which has essentially the two end members of ice. We have the smallest grained ice, which is snow, seen here, lots of surfaces for light to scatter out from, whereas this large grained ice, this blue marine ice, which is caused by freezing of liquid water, is so smooth that you only see that kind of blue effect, where the red light is getting absorbed, the blue light makes it all the way to the bottom and gets reflected back up to us. So this really got me thinking when I was in grad school. If you've got ice that absorbs a lot of redder wavelength light, and you put a planet around a star that emits a lot of longer, redder wavelength light, what could the climate do on those planets compared to planets orbiting stars that emit a lot of shorter, bluer, visible and UV light? And we looked at those planets both in terms of how likely they are to get into these so-called snowball episodes. How likely are they to freeze over? How likely are they to melt if they were in snowball episodes? What we found was that, and here we're looking at how close to the ice, to the equator, the ice can go. So how much it could freeze. If there's no ice, then we have, it's way up here. If it's covered in ice, it's all the way down here. And we sort of, in our simulations, and for people who are climate scientists in the room, what I've used are general circulation models largely to do my work, or global climate models. And these models, they have a dynamical core. They solve a series of nonlinear differential equations which describe atmospheric circulation using global fluid motions and flow. For those who might be more technically minded in the climate science realm, just to let you know. And those simulations, we can start off our planet in what's called a warm start, just like the Earth. And we can slowly dial down the amount of energy the planets receive from their star, and we can see at what point the planet becomes frozen over. We can also start our planets in cold start situations, already frozen over in snowball states, and dial up the amount of light the planet receives from the star and see at what point those planets melt out of their ice-covered conditions. And I was interested in finding out how this melting and freezing would depend on how that light is distributed from the star across the spectrum. And so we looked at M stars, we looked at G stars like our sun, we looked at F stars, a little hotter and brighter than the sun. What we find was that not only are M star planets harder to freeze, but they're also easier to thaw out of snowball states. And therefore they have more stable climates, being harder to freeze and easier to thaw. And that's because of this ice albedo effect, that ice is much more absorptive of the type of light that planets receive from M stars. But the atmosphere is also playing a role, particularly when it comes to what's called Hadley circulation, which is a process on our planet that is responsible for the net transport of heat from areas of energy surplus at the equator to areas of energy deficit at the poles. And what you're seeing here is a sort of cartoon plot of the annual Hadley cell. If I were to show you a seasonal diagram, you'd see one dominant Hadley cell that's responsible for the net transport of heat to the cooler winter hemisphere. And so what we find is that M stars, they're absorbing a lot of energy and radiation also in their atmospheres, because these planets have, M star planets have carbon dioxide, water vapor in their atmospheres, and those absorb a lot of infrared radiation as well. And they're absorbing that radiation, and they're keeping a lot of that energy and heat at the equator instead of transporting it to the north or south. And that allows those planets to sort of melt out of ice-covered states more easily. So there's a lot more that I could say about M dwarf planet habitability. We've put a lot of that into a review paper that I encourage those of you who want to know more about this subject to download and read. It basically sums up all the knowledge that we have, both observationally and theoretically, about the habitability of planets orbiting M stars over the last decade. I also want to mention that we're discovering planets in multi-planet systems, planets that are not alone in their systems, just like our own solar system. And when you have planets that are not alone in their systems, a lot of interesting things can happen. Those planets can push and pull on each other, and that pushing and pulling can cause an evolution in the planet's orbits, which can affect habitability as well. But this environment, the more planets we find in these systems, the more likely this environment is that it might be the place that we look to for the next habitable planet. And a system that gives me a good example of that is Kepler 62, which is a system that's 1,200 light years away, so not possible to follow up on these planets anytime soon, but it's a good test bed for what we might do with planets that we discover with TESS. And so I've looked at, this is a 5-planet system orbiting a K star, so a little hotter and brighter than an M, but not quite as hot and bright as a G, like our sun. And the furthest 2 planets were the most interesting from a habitability standpoint. But this one, given that it's just about to be perfectly in the habitable zone, but not with an atmosphere. If you put an atmosphere on top of that, it's likely too hot. And so the 62F one is the best prospect because although it would need a lot of carbon dioxide to be habitable, it would not kind of get into that regime of being too toasty. And so one of the things that we did was using actual data from Kepler, the Kepler mission. We put that data into our simulations, and we wanted to figure out what would it take for this planet to be habitable, to have liquid water on its surface and have that liquid water stay liquid. And we found, this is an example of the kind of diagrams we can make with our simulations where we look at latitude and longitude. Essentially, it's like a map that we're opening and unfurling flat. And we're looking at surface temperature. And what we find is that you can have open water over a pretty wide swath of this planet in a similar scenario as Earth for high CO2, a high amount of carbon dioxide, but again, plausible where this planet resides in its orbit, with Earth's current axial tilt, its obliquity, and assuming a circular orbit. That gives us a global mean surface temperature similar to modern-day Earth. So this planet, we found, could be habitable. And that's also a very exciting prospect. If it were closer to us, I'd really want us to follow up on it. Most recently, I've looked at other sources of surface compositions and how those surface compositions might respond radiatively to different types of light. And so we've been looking at water ice. We now are looking at water that has a significant amount of sodium chloride, salt in that ice. And this shows you that, for an example, this is a brine pocket, and when you have the brine, the sort of the colder temperatures that you can actually have on certain planets, you end up having something precipitate within your brine pocket. And that salt, which we actually called hydrohalite, which is salt with water, you have the precipitating into a crystal. And that crystal form, that crystallized form, is so much brighter than even snow. And so if we look at albedo, reflectivity, as a function of wavelength for different types of surfaces, ocean, different types of ice, snow, this is hydrohalite here. And you can see that the reflectivity is very high compared to snow at the infrared wavelengths, where M stars emit strongly. And so what we found in our work, which is currently under review, is that if we include parameterizations for this hydrohalite surface type in our models, we find that planets around M stars are likely to be much colder than originally thought. And so this is particularly important for planets that might be kind of in water belt states where they have very narrow swaths of open water at the equator. Planets that might be synchronously rotating, where they have that eyeball pattern. They have a day side that's receiving all the stellar radiation, and the night side's not. On that day side, it can get colder at the north and south poles, and we could have colder temperatures, and therefore this surface type could precipitate in bare sea ice. So what I want to say to wrap up is that we are now in the Earth-sized regime. We found a number of planets that are in this realm, and we're going to be continuing to find more and more planets. And what I'd like to do is to, if you would humor me, all close your eyes for 30 seconds or so. And I'll close my eyes too, so you don't feel self-conscious. And I want you to imagine what the surface of an exoplanet might look like. A new world that we've never seen before. What does that landscape look like when you imagine it? If you were setting foot on that planet, is there an ocean that you can see in the distance? Do you see grass? Are there trees? How many stars do you see in the sky? Is it just one sun? Are there three? Is there life on that planet's surface? What does that life look like? Okay, you can open your eyes. Maybe you imagine something like this. Maybe you imagine something like this. Maybe what you imagine looks nothing like either of these artistic depictions. And the great and exciting thing is that anything that you imagine is possible because we have no idea what these planets are actually going to be like. But the hope is that one day we might actually no longer have simply artist depictions, but actual photographs that look like this, like the Grand Tetons taken by Ansel Adams in 1942. And very lastly, I'd like to mention that it's important to look at these things, to look at the universe in many different types of light. If we were to just look at the Milky Way with visible light, we'd miss out on so much information. Whereas if we look in other types of light, like the infrared, we get so much more. And therefore, it's crucial to be able to encourage young middle school girls of color to see beyond what their eyes can see, beyond what they're being perceived, how they're being perceived, what they think of themselves, to get further and deeper into how they view their world around them and the universe around them. And that's what my organization, Rising Star Girls, is dedicated to, encouraging girls of all colors and backgrounds to explore and discover the universe using theater, writing, and visual art. And we use the creative arts because those arts are inherently personal. And it's a lot easier at times to develop a personal connection to a painting or a poem that you write than it might be to develop that connection right away for an atmospheric trajectory that you might calculate. But the idea is that eventually we want to bring that personal connection to the sciences and to astronomy so that when a girl looks up at the star or a planet that she's learned about and that she's written a poem about, that she actually finds this personal connection that will carry her through as she continues to evolve in her study of the field. So if you'd like to be involved and learn more about Rising Star Girls, please visit our website, risingstargirls.org. We would love to have as many people involved in our efforts as possible. I'd like to acknowledge this lecture series, Ken and James, for this opportunity to be here with you today, and my funding sources and collaborators. Science is never done in a vacuum, and I'm so glad that it's not, because being able to collaborate and generate new ideas with my team members is one of the most exciting things about this field. So thank you so much for your attention. So in our review paper, we talk even more about this topic. The answer is that yes, it's believed that photosynthesis can actually exist on planets orbiting M stars. Of course, it's all theoretical, but there have been people that have been working on this, and that what they find is that, you know, on our planet we have the photosynthetically active radiation that's used is in the visible part of the spectrum. Now, if you have a star that emits largely outside of that spectrum, what we think will happen is that plants will evolve to use the most available photons that they can. And so they will evolve to use the IR photons. If they just might have to step it up and use whatever's available over a much wider range to be able to get the same amount of energy they need to carry out those reactions. Yeah, so this is an interesting point. I mean, and a lot of people would argue that M stars have such disadvantages for life that, you know, why bother? It's much more conducive potentially to life around a planet orbiting a G star. But what I want you to focus on, all of you in the room, is that when we talk about numbers, right, we have hundreds of billions of stars in our own galaxy, and hundreds of billions of galaxies in our universe, right? That's a lot of stars. And if we are wanting to, given that we know that just about every star has a planet, if we're wanting to find, sort of maximize our kind of bang for our buck and find life as early as possible, we need to talk about numbers, and we need to go where we have the numbers. And when it comes to potentially habitable worlds, we're likely to find more of those around the star with the greatest numbers in it. And so that's one of the reasons why we focus on M stars. It's a good point. We could end up finding life on a planet orbiting a star just like ours. But also the other thing is that those M stars have those long lifetimes. And so that's another, in my book, really good kind of pro on the side of life for M stars. And of course, the detectability issue as well. But nearby solar neighborhood, M stars are more plentiful. So astrobiologists are currently looking at that. I'm not looking at that, but there are those who are chemistry focused and biologists that, because we need to explore alternative metabolisms than the ones that we're used to seeing here on Earth. For example, Titan, Saturn's moon Titan, has liquid in our solar system, but that liquid is not water. It's liquid ethane and methane. If we find life on that moon, it will be like nothing we have ever known. And we could find life in our very own solar system. And so it's important to understand how that life might be able to carry out its metabolic processes and reactions, given that it doesn't use liquid water as its solvent. So it's important, we only have, our N is 1. We only have one example of life, and all life on Earth uses water. So one example of how life carries out its reactions. They're working on it. I don't know that they've come up with an actual metabolic pathway. And there were some questions about potentially life that uses arsenic in place of a different building block, but I think those results may have been a bit questionable, and so I'm not sure where the results stand at this point, but that is an area of active research, and it has to be, because we don't want to miss discovering life because we're too Earth-focused. Right? It's an important point. Well, I like the transit method in particular. Of course, direct imaging would be, I want to take a picture of that planet. I want to be able to get that Ansel Adams photograph. But direct imaging is incredibly difficult for these Earth-sized planets. And so barring that, I would say the transit technique, because it gives us size information. The Doppler technique is useful because it gives mass, but we don't get an exact mass. We get sort of limits on the mass. But transit technique can actually give us size information and something called transit timing variations, where if you have multiple planets in a system, the transits that we measure can actually happen a little bit off what we would expect. And that's because other planets are in the system pushing and pulling and kind of delaying that what we would measure as the transit. That can tell us that other planets are there, right? So that technique alone gives us a lot of information that I would like to see, and I'm glad that we are doing the test mission. We're going to be using that technique much more broadly. Yes, so it's a great point that the way that planets form around different types of stars is different. So another issue with planets around M stars is that because M stars are smaller, they're made from smaller protostellar disk, and so they're made out of less amount of stuff. And so if you've got less stuff that you need to make the planet, your planet could be too small to be able to generate its own dynamo. So the magnetic field could be weaker, and that's an issue because you need a strong magnetic field to be able to protect your planet from the harmful stellar radiation. We have a strong magnetic field which helps it protect us from the sun's solar radiation. So that could be an issue in terms of the internal heat source. It might not be as strong or as long-lived on planets orbiting M stars. But other theorists will tell you that there could be ways around that. But that, again, is an area that we're looking into as well. So the Kepler mission, I think it was about 150,000 stars in that one particular patch of sky. But yet, it was one particular patch of sky in the constellation Cygnus. So with I have to look that up, the Cygnus. But TESS is going to be looking at stars that are 30 to 100 times brighter than Kepler. A lot of the stars that Kepler found were hundreds to thousands of light years away. Looking at one patch of sky versus all sky, which is what TESS is going to do once it gets to its orbital location. It's going to be looking across the sky. We expect in the next couple of years, it's a 2-year mission, to be able to find thousands of just Earth regime planets, let alone the other planets that we find. This is another good reason why M-stars are good to look at, because your orbit is much shorter, because to be in the habitable zone, you know, you are closer in to the star, and so the time it takes for you to go around the star is going to be less. And so you need at least a couple, 2 to 3 orbits to be able to confirm a transit. Otherwise, you're kind of in this sort of like candidate planet regime. And so these nearly 4,000 planets have been confirmed because they've had, you know, at least, I think, 2 or 3 orbits to confirm. And so if we were to wait, the person who asked about the G-star, if we were to wait for these transits for planets around G-stars, we're talking, you know, a year, 3 years to confirm a transit, versus for the habitable zone, the orbital period is, you know, anywhere from 15 days to maybe a month, you know, so that takes us a lot less time, and that's really good for being able to generate results fast.
Okay, unfortunately it's 9 o'clock, and you know, some people in the room, like me, have pesky jobs that have to go to. So I want to thank Dr. Shields for spectacular work.
Thank you very much.